part 2 of lesson 33. And let's go back to our PhET demonstration here and continue shining. We'll keep playing it. We'll stick with, let's change the metal. Let's try copper. Oh, copper, interesting. Yeah, how about platinum? Wow, platinum needs a lot of energy. Calcium, let's go with calcium. Calcium seems to be releasing the electrons at a pretty low frequency. Yeah, so it looks like, oh no, it looks, yeah, it is. So violet light is just enough to get them off the surface. So we're shining ultraviolet light on it now. Now let's deal with this electric circuit here. And you can see that the current is presently reading 0.073. Let's increase it so we get a lot of activity. There we go. So now we have a current of 1.474. And what I'm going to do is I'm going to decrease the intensity of the light. And we'll see what happens. Oh, so the current is decreasing. Now, what does that mean? That means just very simply the number of electrons that are reaching the other plate over here is just less. As you can see, there are, oh, so those ones are going really slow. There are just less electrons. But if I increase the intensity of the light, I just get more electrons going over, therefore I get a greater current. So that's one relationship of the photoelectric effect is if you increase the intensity, you increase the current. But what about the speed of the electrons? Let's, you can see some of those electrons are going pretty fast. Let's just decrease the intensity, and you can see there are less electrons, but those electrons are still going at the same speed. There are just less of them. Let's decrease it to almost 0, to 8%. So now we have a few electrons, but some of them are still going really fast. So the intensity of the light is not related to the kinetic energy of these electrons because they have the same amount of kinetic energy. They're going all these different speeds, but there's a maximum speed that these are reaching. So the maximum kinetic energy is not related to the, oh no, I just changed that accidentally. It's not related to the intensity. Okay, so the intensity determines how many electrons or increases the current. Let's go back to that one, higher one. But it is only the frequency that changes the kinetic energy of the electrons. Okay, so there's one concept. Now let's take this and change the voltage on this battery, on this circuit. So now actually we're going, so what happens here? We're making, as you can see, we're making this side really positive, really positive. So now those electrons are going super fast. So what if I make, because now the electrons, we've created a circuit here. We've got parallel plates. This is a negative plate over here, but a positive plate over here. So now the electrons are being ejected from the surface, and the electric field is pulling them over to this plate over here. They're attracted to the positive plate. So all of a sudden, they have a lot more kinetic energy. Let's change that, the configuration of this battery. So we're making it a little, it's still positive, but a little less positive. Okay, now we're going to make it all of a sudden negative. This is a negative plate. Now the positive is switched over to the left side here. And you can see, look what's happening. Oh, some of these electrons are being actually, they're not making it. They're going over that, and then they're turning around and coming back to the positive. Because at this point, they don't have these slow electrons, don't have enough kinetic energy to make it over to complete the circuit here. And they are just being drawn back to the positive plate. And if we continue increasing that, and you can see that the current is going down. Now, why is the current going down now? That's because less electrons are reaching the negative plate over here. So the current's going down, and eventually we're going to get to a point, there it is. There it is. We reached a point at 4.2 volts where there is no current, and even the electrons with the greatest amount of kinetic energy don't have enough energy to make it over to this plate and complete the circuit. So that's why it's reading no current. And this voltage here, let's see if we can, oh, so I just increased it to 3.4. Now we've got a little bit of a current. The magic number that you can find where electrons, where you get a current of 0, looks like it's around here for this metal here, that's called the stopping voltage. So that's what voltage, what's the exact voltage that will not allow electrons to complete this circuit. Okay. We'll pause that and we'll go on to our lesson. So here we have, so Robert Milken did this experiment, and Robert Milken from the famous oil drop experiment, which is coming up. And this is what you just saw in the FET configuration here. And here's the concept of stopping voltage. So the stopping voltage is what voltage will prevent the electrons with the fastest kinetic energy, or the most amount of fastest velocity, the most amount of kinetic energy, what will stop them from completing the circuit. And here is the formula for stopping voltage. It's derived from the formula for voltage. So voltage equals the change in energy divided by the charge. And we're talking about electrons here. Right? So as soon as you see charge, it's always 1.6 times 10 to the negative 19 coulombs. And we rearrange that formula and we get this formula that the change in energy equals Q times the voltage. And then we just adapt it to the principles of the photoelectric effect, and that change in energy is kinetic. And then we're just going to add a stop to this V. So the maximum kinetic energy equals the charge times the stopping voltage. All right, and typical example for that would be example number 3, says determine the maximum kinetic energy of electrons emitted from a zinc surface if they are stopped by a 16 coulomb, newtons per coulomb, uniform electric field over a distance of 3 centimeters. So what do we have here? First, we're trying to calculate the EK max, maximum kinetic energy of these. They are stopped by, this is an electric field. Right? Electric field of 16 newtons per coulomb over a distance of 3 centimeters, or 0.03 meters. So again, we have parallel plates here. Parallel plates, one's positive, one's negative, and in this case, the electrons must be going that way, because if they were going that way, then they would be attracted to the positive plate. So they must be going that way. Doesn't make a difference. We're just dealing with parallel plates, and what we need to know is the voltage between these plates. So in step 1, we can calculate the voltage between the plates, and that will be the stopping voltage, because it says if they are stopped by a 16 Newton per Coulomb uniform electric field. So in step 1, we're going to go back to our electrostatics unit and use this formula to calculate the voltage. Which equals 0.48 volts. So that's the stopping voltage. And then we can, in step 2, we can go to the formula we just worked on. And then it just becomes the charge of the electron. Times the stopping voltage, and that is going to yield an answer of 7.7 times 10 to the negative 20 joules. And note, we're always dealing with energies that are extremely small, because we're talking about the energy of a single electron. So very small energies, you should be getting to these answers. Okay, last thing, and perhaps the most important, is called this, the photoelectric formula, the biggie. And as I said at the beginning of this lesson, the photoelectric effect is an example of the conservation of energy. So here's how we set it up. We have the input energy. Now that's the energy from the light source. So the light That's the energy, that's the formula for the energy of the light source, and that's your input energy. And then the outcoming energy, so on one side we have energy in, and on this side here we have energy out. The outcoming energy is the energy that the electrons have ejected, plus the energy that you need to give the electrons to get them off the work surface, off the surface of the metal. In other words, the work function. All right, got that? Let's review that again. So this is the energy we put in. That's the energy of the light shining on the metal. The energy on the other side, the energy output, is the kinetic energy of the electrons, plus the energy that you need to get them off the surface, the work function. That's a conservation of energy. The energy in equals the energy out. All right, now I usually write this formula as follows. I'm just going to solve it for EK max. So if I solve that for EK max, I get this. EK max equals HF minus the work function. It doesn't matter which way you write it, as long as you understand that it's a conservation of energy. And usually, because usually what they're going to be asking these questions is what's the velocity of electron, or what's the maximum kinetic energy of electron. So I solved it for this, and this says that the incoming light, the energy of the incoming light right here, this is the energy of the incoming light, but you've got to subtract from that the energy you need to get the electron off the surface. Okay, so given that, we can now do a problem. It says a threshold frequency of silver is 1.4, so threshold frequency 1.14 times 10 to the 15 hertz. That's the threshold frequency of the metal. Then we shine EMR on the silver, and the wavelength of that EMR is 2.5 times 10. 7 meters. Strikes a piece of silver, determine the speed of the electron. So we're trying to find the velocity. Now, to find the velocity, what we need is the EK max first, because then we can just use EK equals 1/2 mv squared to find out the velocity. So we're going to go to our formula that we just derived. Right, and then we're going to expand the formula. And in this case, we're given a wavelength, so it's going to be h c over lambda naught. Sorry, that is absolutely incorrect. We're given the frequency, the threshold frequency. My apologies. We'll erase that. That makes things actually a little easier. HFO. What we're given is this one here. We're given the wavelength of the incoming light, so we're actually going to have to change this part of the formula. There we go. That's better. Okay, so this is, you have to be very careful, because I just made the mistake that I'm trying to warn you against making. This is the incoming light. This part of the formula right here is always the incoming EMR. And in this case, they give you the wavelength of the incoming EMR, and therefore you have to change that part of the formula to HC over lambda. And then they give you the threshold frequency, and that will always occur there. So don't get those confused as I just did. And then we can just plug in the numbers, and well, let's do it just so you can see it. Oh, small. Oh. I knew I was going to run it. 1.15 E15. Sorry, that's a mess, but you get the points. Just wanted to make sure you're plugging in the numbers into the correct area of the formula, and then get the answer, which turns out to be 3.98 times 10 to the negative 20 joules. Now that's the maximum kinetic energy of the electron. So that's one of the electrons that would be right at the surface. It would have the maximum amount of speed. And then we can go to EK max equals 1/2 mv squared, and solve for V. 2 EK over m square root. Plug that in for your EK, your mass, we're talking about electrons. So your mass is going to be 9.11 times 10 to the negative 31. And eventually you will get an answer. Now these electrons, they're whipping off that metal pretty darn fast. So you should be getting relatively large numbers. And you end up getting 2.96 times 10 to the 5 meters per second, which is insanely fast. 9. All right, so that ends the photoelectric effect. And just to review, the photoelectric effect for the second part of the lesson is really a conservation of energy concept. All right, on to lesson 33.